Everyone. In this video, we're going to introduce the idea of a normal distribution. So let's look at the histogram that's shown here, where we have some measured value, which in this instance is taking values between -16 and +16. And we have a histogram showing the frequency of each of those values, or a bar chart showing the frequency of each of those values. So that shape, that distinctive bell shape, that's really common when we have large sets of continuous data. So height distributions, age distributions in populations can look like this. Grade distributions amongst large groups of people. These are called normal distributions. In these distributions, the mean, median, and the mode are all in the center, so 0 on this diagram. So that would be the mean, the median, and the mode. They're all equal to each other. So the most common value is found right in the middle, and the mean and the median have the same value as well. Everything else is distributed symmetrically around the mean. So we usually define a normal distribution by its mean and its standard deviation. So those are the defining characteristics. If we're trying to show that a random variable, so x, for example, which could represent heights or grades or whatever, to show that it's normally distributed, we use this sort of notation. So that little squiggle thing means like is distributed. So x is distributed. And for the normal distribution, we will do a different type of distribution next year, which is the binomial distribution. And in university, you'll probably study others. Poisson is a very common one, a Poisson distribution. But then we give its parameters. So x is normally distributed with a mean of whatever, and a standard deviation. Now, technically, it gives the variance. But because we so rarely use variance, we give the standard deviation as a square. So to illustrate what that means, if I had a distribution, so let's say I have some variable y that is distributed normally with a mean of 76 and a standard deviation of 8, I would write it as 8 squared. So technically, I could write it as 76/64. But since the standard deviation is the thing I really want to know and not the variance, we write the 8 with the squared just to make sure we know the information we're talking about. So when you see that notation, it means it's a normal distribution. The first number given will be the mean and then the standard deviation. The other thing about a normal distribution is not only is it symmetrically distributed, but it's distributed such that certain percentages of data fall within a certain distance of the mean. So if this graph here represents a normal distribution with a mean of 0, so the mean, or remember our other notation for that is mu, is 0. The median is also 0 here, but with normal distributions, we tend to just talk about the mean because it's the same as the median. And the distances here are divided in standard deviations. So +1 would mean we are 1 standard deviation above the mean. 2 would be 2 standard deviations above the mean. -3 would be 3 standard deviations below the mean. So a distance of 3 times the standard deviation below the mean. Then these are roughly the percentages that we expect to see in each of those gaps. So between 1 standard deviation below the mean and 1 standard deviation above the mean, we expect to see about 68%, or a little more than 2/3 of the data. Going out a little bit further, we get to about 95% of the data is less than 2 standard deviations from the mean. You do not have to memorize these percentages. Later on, we'll learn how to find them on our calculator. So let's look at an example. We have a normal distribution. So x is distributed normally with a mean of 192 and a standard deviation of 9. So if I were to put those numbers on this table up here, 192 would be in the middle, and the gaps, the intervals that I would be using would be distances of 9, because that is the standard deviation. So I would add 9 to get to the next line, so this would represent 201. And then I would add another 9, so this would be 210. I would add another 9, so 219. And I'm expecting very close, like 99% of my data is going to be less than that number. And going in the other direction, if I'm subtracting 9, so 183 would be 1 standard deviation below the mean. Let's subtract another 9, so 174 would be 2 standard deviations below the mean. And minus another 9, so I would get 165. Would be 3 standard deviations below the mean. The vast majority of the numbers in this distribution are therefore going to be found between 165 and 219. If I find a number less than 165 or a number that's bigger than 219, that is an extraordinary value. That's a surprising value. I don't normally expect to find numbers more than 3 standard deviations away from the mean. So the percentage of the values that would be found between 183 and 201, that's going to be in this region here, would be my 68%. Between 174 and 210, well, I add another 13.5% on each side, so another 27 altogether. So that is 95% of the data. Now, you'll notice if I add the rest of this, it tells me that 100% of the data, if I add the 2.5s on, is going to be between 3 standard deviations. And that's not true. It's something like 99.8. But because of rounding here, because we're only giving to the nearest tenth, it ends up looking pretty close to 100. And that's because it's so rare to find numbers outside of that.